In this video, I'm looking at the approximations that we use in weak acid calculations. So we're going to start by looking at the weak monobasic acid HA. So HA is just the generic formula for a weak monobasic acid. And remember that we only have to do weak monobasic acid calculations at A level. So because it's a weak acid, it's going to dissociate partially into its ions. So we have a one-to-one relationship there between H plus and A minus ions. That's going to come back later on in the video. So from that we can write the Ka expression. The equilibrium constant for this acid is equal to the H plus concentration multiplied by the A minus concentration all over the concentration of HA. Now remember that the square brackets refer to equilibrium concentration. So I'm just going to focus on the acid for now. So that is the concentration, technically that's a concentration of the weak acid at equilibrium. So here's the first approximation we're going to use. Because the dissociation of that acid is so very small, it's typically no more than 1%, we're allowed to use this approximation. The concentration of the acid at equilibrium we're saying is the same as the concentration of the acid before it's dissociated, i.e. its original concentration. So the Ka expression doesn't change, but we just need to be aware of the fact that the HA concentration we're going to use in the calculation is allowed to be the original concentration of the acid. Now we're not quite finished because the water that's present, these are all aqueous, remember, the water that's present is also dissociating according to that equation there. So the water is dissociating into its ions, H plus and OH minus. So there's the Ka expression. Again, we're going to focus now on the H plus concentration because technically that is a combination of the dissociation of the acid and the water. So remember, the acid dissociates into its ions, H plus and A minus, and the water dissociates into its ions, H plus and OH minus. So this H plus concentration here is coming from both of those. But what we've got to bear in mind is the water is so hardly dissociated, way less than the acid, we're allowed to make the approximation that the H plus concentration at equilibrium is the same as the H plus concentration of the acid only. So we're ignoring the tiny amount of H plus ions coming from the dissociation of water. And then the final approximation, because of what we've just said there, the H plus concentration, which is from the acid only, we can therefore say is the same as the A minus concentration, and that's coming from that 1-to-1 ratio from your monobasic acid. And so therefore, we'll just summarize it now, the Ka expression can be simplified to the H plus concentration squared, so that's the H plus concentration from the acid only, all over the concentration of HA, which we've already said is the original concentration of the weak acid. And then obviously if you were going on to calculate the pH of the weak acid, you would rearrange for the H plus concentration, so you would get that, the square root of Ka multiplied by the HA concentration, and then the pH is minus log of the H plus concentration. So I thought we'd finish by looking at when the approximation may no longer work. So you might be asked to suggest when the approximation isn't valid anymore. So if you think about what's at the center of the approximation, it's all centering around the fact that the weak acid is so hardly dissociated. So if there's a greater extent of dissociation, then the approximation sort of gets less and less valid. So in other words, we're talking about the weak acid gets stronger. Now there is something called the 5% rule. So what it essentially says is once the dissociation or the level of dissociation gets above the 5% mark, then we can't use the approximation. So if you remember back to the start of the video, I said typically weak acids are only about 1% dissociated. So I just thought we'd do a quick ice comparison of 1% dissociation versus 5% dissociation. both for the same weak monobasic acid, HA. And just a quick reminder that the I stands for initial moles, C stands for the change in moles, and E stands for the equilibrium moles. So if we say both of the acids have the same concentration, so 1 mole per decimeter cubed, I'm saying here, we've initially got 1 mole per decimeter cubed of HA and 0 of H plus and A minus. So in the case of the 1% dissociation, there's going to be a change in the moles, or the change in the concentration, by 0.01, so it's going to drop minus 0.01, and the 5% is going to drop by 0.05, so 1% of 1 and 5% of 1. So that means that the H plus concentration and A minus concentrations, so for 1% are going to go up by that amount, 5% by that amount. But what we're really interested in is the equilibrium moles or equilibrium concentration of the acid compared to the original concentration. So you can see that in the 1% case, the equilibrium moles or concentration of HA is very, very similar to the original concentration or initial concentration. Whereas here, the 5% rule would say, no, that's too different, we can't make the approximation anymore. So in the case of 1% dissociation, it's okay to say that the HA concentration at equilibrium is the same as the undissociated HA, whereas 5%, it's no longer possible to say that.